Good morning everyone and welcome back to the new video. This video is based on chapter 4 of John Searle book where we will cover most important type of concept, that is Brownian motion or a Wiener process, and also cover the stochastic differential equation for stock price and in stock the modeling of stock price in continuous time. In previous chapter, in a binomial chapter, we learn about how to derive the stock price of with discrete model, that is binomial model, and in this model we will use continuous time model or continuous time differential equation to solve the problem of financial to model the stock price, right? So let's go back to our board and start with the new concept, and I am very excited to show you this concept. So let's start with some basic terminology. Okay, discrete time and continuous time. Okay, so discrete time you can understand, like it is happening, any process is happening after some interval, right? There is a fixed gap between the interval, right? That we can call as a dt. It is 0 by t, and the process go like this from here, then here, then here, and then here. So you can model it is a random walk, and you can see it look like binomial tree. But in continuous time, right, the process can go anywhere, so it is changing with respect to time continuously, right? So it is very easy to model discrete time, and then it is very hard to model the continuous time because we don't know, there is uncertainty required, there is uncertainty on y-axis. Also there is uncertainty in y-axis too in discrete time, but there is uncertainty in x-axis, in time axis, right? So we usually discretize the continuous time using a discretization scheme like Euler and Myristin. You will run in financial engineering, Myristin. So we will convert the stochastic differential equation. This is the stochastic differential equation. Uh, this is the mu term, mu s dt plus s sigma, and this is a Brownian term, dz. So let me show you again. I will discuss you what's the stochastic differential equation, so you understood. So in discrete time, the the variable that change is discrete variable, and in continuous time it is called continuous variable, right? So let's go on our first process or first property, Markov property. So see, Markov property tells that the process or the information of past doesn't matter, or the, let's say, stock is gone up, down, up, down, up, down, and we are at this at t. So at t, all the processes or the past history doesn't matter, all the information of future is stored in at t. So let's say today is t and the stock price is trading at 100, and previous day it was 90, previous day it was 70, and day before it was 100. So it was like this 100, and we discretize it to make the visualization simple. It is t, that is sorry, t minus 1, t minus 2, and t minus t here. And we said at it previous time it was 90, 70, sorry, this is 90 and this is 70, and we were at 90, then we gone down to 70 and gone up to 100. This was the past history, and there was some history there. So at t we can't say that if the stock price, the technical analysis people who so many people do the technical analysis. So they set a history of the future of the stock process is based on the past history, but for modeling perspective we don't think that. We think that all the information of future is stored at t. So the past doesn't matter, so it doesn't matter that it make v shape and it will go also make w shape. There is v shape, w shape, l shape, right? So it doesn't matter, and all the information of future is stored in 100. From here it can go to anywhere, right? The probability distribution is like this. So that's the, yeah. So the more formal intro is type of stochastic process where only current value of a variable is relevant for predicting the stock price. And that's how all the Markov property in one term you can remember, right? Past doesn't matter, all the value is stored on current price, or future future important value or prediction is stored at current price. Okay, so let's go to continuous time stochastic differential equation. So continuous time, in Markov property, Markov in continuous time, it's follow random normal distribution with mean 0 and variance 1. So let me tell you the psi. This means the discrete continuous variable is derived from normal distribution. So let me give you intuition how it's work, right? So there is a mean of a process. Right, there is a mean of process. Mean of process means it set the level of the stock price. If mean is 0, then it is a constant like this. If mean is little bit up, it can go like this. If mean is down, negative or anything, it go like this. So this is the mean of the process, right? And the variance means the uncertainty. So mu is mean, or you can say m, right? And variance is 1 variance means the value is variance means uncertainty, right? Expected of x square minus whole x square, right? Expect minus whole x square. Let me check. This formula is very, and it is a standard derivation of variance is sigma. So sigma is volatility. Volatility means how uncertainty it is. So let's say volatility 30%. So it means that the uncertainty is at a rate of 0.3%. So how this will change? So in continuous time it will change like this. If mean is 0, 10 and volatility is 30%, then it will change with respect to 30%, right? And that it is like, so it is called, there is a drift term. So mean is drift term, and second is volatility term, and variance term or volatility term. So another term is volatility term. So SD, stochastic differential equation, consists of a mean term or drift term plus variance term. That's how we model it. And let's say, so for Markov process, let's say it is 10, it is the stock price going at 10, and change is with normal distribution of mean 0 and this is 1. So the Markov process would look like this because there is no drift term and its probability would look like this. Let me erase it. Because there is no drift term. We want drift term. And it is changing with the rate of 1 year, right? Because the variance is 1 year. And the standard deviation would be like this. Polarity would be one like this. And yeah, that's the continuous time model. And we can discretize it or make the timestamp so smaller. So that would be delta t, right? And yeah, so the simple Markov, let's say Markov formula can be a random, let's say for random t, that would be equal to normal distribution with mean 0 and variance t. Yeah, that's how simple it is. And let's go with the Wiener process. So you understood that Markov property and the normal distribution mean that like this is normal distribution, here is a mean, and variance is t or sigma root t, that is rate of change, right? Variance is t and this is variance. So you can understand that all the random data, random continuous time variable is coming from this distribution, right? Let's say it is distribution from 10 to mean is 0, right? And let's say between 10 to 100, and all the random number is generating 0 to 1. It can't be 10 to 100, right? So let's say first number is 0.6, second is 0.1. So the process is going like 0.6, then 0.1, then next number from a distribution is 0.4, then 0.4, then 0.5, 0.01, again down. So we are drawing the number from random distribution and going, and let's say we are plotting it. Okay, and let's go to Wiener process or Brownian motion. I like to call it Brownian motion. Okay, so simple. Let's go back to the physics concept, right? The Brownian motion was first discovered by physicists, and it is used for modeling the random movement of nucleus or atom in a molecule. So we all know that the molecule atoms are what is vibrating, always vibrating, are not on rest. So how they are vibrating, the random, to capture the randomness of the molecule, we use Brownian motion and was discovered for it. And then it was first, let me tell you the history of Brownian motion, right? I don't know Robert Brownian. Okay, let me tell you. In 1827, the Robert Brown noticed a Polian steed suspended in water and move irregularly, swimming the yeah. Okay, let me explain you. So in 1827, there was a man, a scientist or physicist, Robert Brown. So he discovered that he took a jar of water, right? A transparent jar of water, and you can even try it. Let me show you on camera. That would be easy to understand it. Let me show you in camera. So yeah, I got a jar of water, right? You can see it, and I have a groundnut with me. You can understand it like a molecule or a anything. So give a let's do a experiment where we put this groundnut in the water and see how it goes down to the bottom. So let me put the first. You can see. So you can see it is moving uncertainty. Every time if I put it from a same place and I with same everything same, it will go to different part and it is moving right. So let me do it again. So yeah, see all the part going down and the way it going is random. Okay, let me put 2. You can observe this phenomenon with rice very what person very well, but I don't have a rice right now. So you observe that. So let me go back to my board. So I put my groundnut here and it is following random path, right? In second experiment it follow this part little bit here, and in third experiment it follow this part. And he was like, why this is happening? So he couldn't understand it, but he noted this phenomena as a Brownian motion. And in let me check my fact motion. Einstein then respond to a tiny invisible particle which suspend to liquid atom was okay. So after that, after Fourier, Einstein solved this mystery, and he told that the the force, molecular force by water that is exerted or applied on the side of grain is random. So from at this point, the force is here. From molecule, the force is more at left side. So it move like this. At this point, the force is more from this side. So that's why it move right. From here, the force is more from up. So it go down and like this. You can understand the molecular force are uh, exerted on particle from all the spaces. Like so, you can't physically predict that where it goes. So we derive a phenomenon on mathematics to model that, and that model process is called Brownian motion. So it is observed in physics to, let's say, Brownian motion Brownian motion of molecule in physics video. I don't know. Should I get a copyright strike?
Small and are supported by a fluid. In this case, that fluid is a gas. You are
okay. Yeah, it's random, right? And in finance, we use this randomness to predict the randomness of stock market. To model the predict is not the right word, to model the randomness of stock movement, because nobody can model the emotion or a sentiment of people. So we model the randomness. See how this random, and this is done with Brownian motion, and it have 3 property. First is it always start from 0, right? First is it start from 0. Second property is the small change in time. Let's say this small change in this time dt. It's standard, it normally distributed, right? It's from normal distribution. The variable is from normal distribution, with mean 0 and variance 1, right? The change of time, we draw the random continuous time variable from normal distribution. And third is, so the value of dt at two different interval should be independent and normally distributed. So let me explain you normally distributed. First, let's say our process is like this. Okay, we are at we look at dt, right? One part is here and second part is here, right? So these two part are interdependent. It doesn't depend on the past because it's for a Markov property. So these are interdependent, and if you plot this like this difference, right, it would be normally distributed. The difference in both random variable would be normally distributed like this. This is will be also normally distributed. So that's the Brownian motion and its simple part. So it is denoted by, in many book it is denoted by wt, but in this book it is denoted by epsilon, right? So the epsilon or z, right? So the change in small period, so change in small time is equal to, this is some constant epsilon, where epsilon is normally distributed constant with, sorry, unable to see. Why my net is not working? What the? Yeah, we are on back. So this is the Brownian motion, and it is derived from normal distributed variable, that is normal distributed variable with 0 1, mean 0, variance 1, and it multiply with respect to variance or standard deviation of time dt. So in simple term, z or wt equal to epsilon dt. That's the Brownian motion. And yeah, that's simple it is. And another formula for it is, I said it is independent, right? So z at t, Brownian motion at t, and z at 0 would be just the summation of n and all the variable that is used to derive the process till n, and with respect to dt. And that's simple it is very simple concept. Just it is a new concept that no very few people have heard it before entering into quantitative finance. That's why it sound hard, but trust me, it is the core of quant finance, and it is very easy to run it. Okay, now we generalize this. Generalized Brownian motion, and I can show you the code. I will show you the code, and I will make another video on the projects. So in my projects there is a modeling of Brownian motion, arithmetic Brownian motion, geometric Brownian motion, with q measure and p measure, and I will show you that. And generalized stochastic process, you have to understand it is like Brownian motion with drift term plus variance rate or variance term. I told you, right? So you can understand as a dx equal to a dt plus b dz, right? So here in this is a generalized Brownian motion, and it is in a discrete time. And let me simplify you. A and D is some constant. A and D is some constant. Okay, and you can understand like, okay, this is the drift term and this is the variance term, right? And all the uncertainty of term used is combination of drift term and a variance term. That is Brownian motion with some alpha drift, some beta variance, and alpha beta is variable or a constant, and that's how simple it is. And you can, if there is a no variance, let's say if there is a no variance, that would be dx equal to a dt, right? Because no variance equal to 0, a dt. And if we rearrange it, that would be a dt, dx by dt equal to a, right? And if we integrate it, we do integration at both sides, that would be 80, and this would be x because 1 x, so that would be x equal to an xo plus dt. I don't entirely sure how this integration worked, but the final output is xo plus 80, and that makes sense, right? So the next term of a Brownian motion is addition of a previous term. Xo is the current term plus some uncertainty 80, some variable. Okay, that's simple to understand it. Yeah, and if we take a very small timestamp like delta t, then this would be changed into delta x equal to a, our at plus b epsilon variance term, right? And then our mean of delta x would be a at, that is our mean, that is our standard deviation or variance, standard deviation, and our variance would be b square delta d, right? And our standard deviation is b upon delta t, and that's simple it is. Okay, so the effect of t, delta t, right? Let's see effect of delta t. If delta t is big, very big, so the change would be very big, like this, right? If delta t is medium, let's say it is medium, and the change would be nice but not so much. If it is very small, then it would be continuous change, like this. So effect of delta t is very important. So we generally take the dt value of 0.0001, right? So change, or dt value equal to time divided by n, number of steps. If the number of steps is 1000, then it would be like, yeah, it's simple it is. And I showed you the generalized Brownian motion. Let me show you the again. This graph is very important. Dx equal to a dt and b dz. This is our drift term and this is our variance term or a standard deviation, right? If there is a drift of a dt and this is linear line of a dt where dx equal to like a dt, it is a linear line. And if we add uncertainty, like if we add this, so it would be follow this line, right? It will be as close as this. You can think like a mean reverting process that is going following the same path. If there is, let's say, no mean, only Brownian motion, right? No standard deviation, only Brownian motion, then it can go negative 2, right? the stock price cannot be negative. So this example was arithmetic Brownian motion. That value can be negative, but in we use geometric Brownian motion, we use rock normal distribution, rock of stock price, right? So we use rock value, so rock value cannot be negative. That's why we use geometric Brownian motion, so that the stock price couldn't go reach this value. So it will be about like this, about the x-axis. Okay, let's go to Ito process. And frankly, I am speaking, let me tell you, the Ito process, it took me 6 to 8 months to solve it. I couldn't understand it. What we say, I couldn't understand it in 1 month or in one read. I don't know why. It was so simple, but it took me 8 to 9 months to understand it and actually solve it. So I will give you some tips or a thing to remember. So consider Ito process. So let me tell you characteristic of Ito process. So ChatGPT, right? Characteristic of Ito process. So this is looking so hard, right? Let me tell you, it is very simple. So adaptive filtration, continuous part, no differential part, non derived. So one property of Brownian motion is like it is differential at every point. You can find the derivatives of process or rate of change of time at every point. That's why Brownian motion is used, because it is continuous time. There is no break. There is no break like limit of 0 t or break of anything. So that's the and Ito process is local marketing. I think drift is okay. Okay. So you can understand it Ito process. So Ito process is XO plus some mu, and that mu would be the function of s function of xt a dt plus some variance, that would be also function of stock price and time. S is what is S? And here is a Brownian motion. Right? Notation can be different, but main logic would be same. This is the initial stock price plus we will add the drift term, and drift term would be a some function of mu, stock price and time price, right? Log of, so any stock price is 100, so we log of 100 would go into this. You can understand like a box where input is anything, input is something and the output is anything, right? So it is like a function f where input is 100 and the function is log function, and that gives us uh log of 100. I don't know what is the log value of 100, but log value of 100. So the process is not constant, constant term process. It is some function, and sigma is also the function. The sigma is also the log function of random normal variable, let's say, and that's the process, and it is differentiable. So you can differentiate and do the stochastic calculus, the calculus used to solve. And let me tell you the difference between the classical calculus and stochastic calculus, right? Classical calculus and stochastic calculus. So in classical calculus, like let's say derivative of x square, right? So derivative of x square is 2x, right? But in if you study calculus deeply, you would know that it is not always a 2x. It's some second order term of x. It is second order term, right? X second order of 2x would be 2. You have to understand the, like, it is wrong, but you have to understand the Taylor series expansor. Let me tell you Taylor series expansor. Okay. So Taylor series is a function approximator. So any continuous time, if we don't have the value or the what we said derivative, we can approximate any function, line function, curve function, anything. It is a function approximator. In classical, the expanding function around point x is Taylor series. Like you can see fx the function, and then we will derivative, and there will be the some term of second order of Taylor series, right? When the take the derivative, especially in differential equation, we ignore higher order term like x square. We ignore this because its value is very small. You can see the delta. You can see the delta x, that is very small, and it generally tend to be zero faster. So how we expand the term, it will go to zero faster. So in classical calculus, we say that derivative of this is directly, let's, it is finite differential method, but the derivative of fx would be derivative of x, right? Simple point. But in Taylor series expansion in stochastic calculus, so we are dealing with rate of change of time, right? And the rock normal property of stocks or many things. So the if we add every part or every continuous variable, the second order term become so big. Second order term becomes so big, became big. So it is not zero, it's some non-zero value, and we can't ignore it because it uh, the value it gives the error, and it is not good to ignore it. So we used it in, or we what we incorporate, sorry, we integrate this second order term with respect to Ito's lemma and Ito's formula. So Ito's formula, I am I don't, let me see I am doing right or wrong. So first we have with respect to the partial derivative of s, then we have partial derivative of s with respect to mu, and that is s with respect to s. Then we have half of partial uh, derivative with respect to s, and that is also s, and this is dot dt plus mu, and plus, sorry, s sigma Volatility term and Brownian motion, and we have with respect to s. right? You can consider it here g is a function of s. I will tell you. So this formula come from the Taylor series expansor. You can see this higher order term, or so, this is second partial derivative. Sorry, this is the second partial derivative, and this is the first partial derivative. So this came from the Taylor series expansor. Let me show you. Yeah, see, df by dt with respect to the function is df with respect to f dt, then df by with respect to x and dxt, and half second order derivative of this with respect to xt, sure. And this is our process stochastic differential equation, and I am not going deep into Ito's calculus. Maybe I would cover it in another chapter, and I would solve some basic stochastic differential equation like this. It is simple. So you understood what is Ito process. So Ito's process is differentiable at all time. We have a function mu, function of st, and volatility of xt, and that's how simple it is. Yeah. Let's model the stock price. Let's find the stochastic differential equation of stock price, right? So the stock price, we can't use simple Brownian motion because there is only variance term. There is no drift term. So we need drift term, right, to model it. So drift plus variance. We have to remember this. But the drift should be adding to the initial stock price, right? So we use mu is our drift term, and the s is our stock price today, right? Our stock price today, and then we will capture it with respect to time dt. So we will see it this at small. So you have to understand, you don't have to be scared with maths. For me, I was so scared that I couldn't understand this notation. But you have to understand it conceptually, or you have to start imagining it. You are a good mathematician if you can you if you can imagine. Imagination is everything. So for me, dt, whenever I think dt, I think of small time step and a very small time step in a graph. So I say change in this gap between this gap, right? So here whenever I see dt, I say change. So we have to capture what change? We have to capture the drift change of stock price. So we have to capture this change, drift change. I think like it might not be mathematical correct. I don't know. I'm just a student. For me, intuition work like this, and it helped me to understand the concept, right? And plus we have to also capture the volatility. So volatility that would add to the stock price, and also what percentage, 0.1, 0.2, how how the volatility should increase, some randomness. So randomness would be given by Brownian motion like dz, and dz is our Brownian motion. So our final would be s dot dt plus s dz, and that's the stochastic differential equation used in most of case for modeling the stock price. That's how it's simple it is, right? Okay, I covered the theory part, and now let's set discrete time. So this is the continuous time. We don't know the what is the change, what time it is, or what stock price it is. So we have to discretize it, right? And I think there it is Euler discretization in the book. They didn't mention it because it is the high concept, and I am very eager to run the Steve Evan book. After this book, we will start Steve's book. First, we will do the discrete time model, and second, we will do the continuous time model, and that would be very mathematical intensive, and I am very excited for it. Okay. So discrete time model. So we discretize it with geometric Brownian motion delta S with respect to S, and then our Brownian motion delta T, because variance is delta T, and our final answer would be this. So small change in spice stock price is equal to like this. Mean drift term, variance term, and it's simple it is. And dt is very small value, like very very small value. And yeah, and this, so you can understand, like dt is here, and every dt till t. So every dt it will give us one value, then it will give us second value, third value, fourth value, fifth value, fifth value, and this will be differentiable. It would be normally distributed because we uh, took the random variable from normal distributed, and it would be non-negative because it is a log form. We took the log form, I guess. We will took the log form in geometric Brownian motion. Okay. Yeah. And let's discuss the Monte Carlo simulation. Right. Let me show you now only. So here I had a project, and I would show you the code also. Arithmetic and geometric Brownian motion. Let me show you the notebook. Why the Wi-Fi sucks so much? So we solved the arithmetic Brownian motion, right, with respect to xt, mu, dt plus this, and the geometric Brownian motion is this is geometric Brownian motion. I can't draw. So yeah, it's pretty same, right? Geometric Brownian motion, and I would derive this equation. So this is continuous time, and we will apply Ito's lemma to find the dynamics of stock price. The term dynamics means that how it is changed with respect to time. We discretize this, or we find the formula if we put the value, and then it will give the output. And I would solve the Ito lemma of this for you. And let's say this is our Brownian motion, UST and sigma ST DWT, and then Monte Carlo simulation. Okay, for you Monte Carlo simulation, it is so simple. It is just a for loop. If you are from a coding background, you have to think of for loop that can derive a possible path for every outcome. Let me show you. So generally there is a number of paths. If we say number of paths is 500, then the code will, let's say for geometric Brownian motion, the code will derive 500 value, different random value from normal distribution, and would put the value in our geometric Brownian motion equation, and would gives us 500 output, different output of GBM. So our output would be, one part would be like this, second part would be like this, third part would be like this, fourth part would be like this, fifth part, sixth part, 7, 8, 9, 10, and this way. So every part is random, and for pricing the option, we took the expectation at last. So our expectation would be at last, and we would find the price of option. Like for binomial, we say na it is 50 to 100. So we will find the normal distribution factor. What is the probability of going price from one standard deviation to two standard deviation, or between one standard deviation to next standard deviation, or confidence interval of 66%, 97%, like that. It is used in risk management, used in pricing of exotic option, pricing of option, and CVA, everything. Monte Carlo is just a for loop that analyze all the possible outcome and help us to find the expectation at the end. And that is the Monte Carlo simulation. Let me code show you arithmetic Brownian motion. Okay, this is our NumPy library, right? Simple. And matplotlib to plot it. And firstly, I should run the app. It would take time. Okay, let's go back to our. So Z is our random normal distribution. Let's say see the function take the number of part, how many paths we want of Monte Carlo similar number of steps. T is time, R is interest rate or return, risk free rate, and sigma is our volatility, and SO is our stock price, current stock price. Simple. And Z is random. So our Z store the random normal. Sorry. Let me show you our how the data type look. Z store our value from number of paths to number of stems. So for paths 1, the value is stored 0.1, 2, 0.3, 3, 0.4. It start from 0. That it start from 0. That's why we start plus 1 number of steps. If the steps is 500, so there would be 500 value. If 1000, there would be 1000 random variable. The outcome would be, let me show you the outcome in code. After X is our stock price, how the stock price, sorry, X is our, look, what is X? Yeah, X is our final stochastic differential equation. Okay, X is our final stochastic differential equation. S is our stock price. Okay, okay, okay. I was thinking why this was happening. Sorry. So our, let me see the plotting. So we plot down in ST, okay, and XT. XT is our arithmetic Brownian motion, and S is our geometric Brownian motion. Sorry, I just forgot what I wrote. So S is our arithmetic Brownian motion, and S is our geometric Brownian motion. Time we made a time array of dt, number of steps plus 1. So we have a 500 like this, and XO is our starting price. So let's see, XO is a log of SO. We took a log price for SO, right? And dt is t divided by number of steps. We found the dt value, and our for loop start from 0 to 100 if number of 1 is zi equal to mean, and this is normalized, so we don't have to capture the whole jump and down. So we normalized the value to 100. Value is big, right? So we normalized all the value between 0 to 1, because after denormalize or multiplying the with the normalized factor, the answer would be same. So we normalized it for continuous, let's say, sorry, for plotting and computationally advantageous, right? You know the so you know the normalized, if you done the machine learning, we normalize the numerical data to make the computational fast, right? So you can see that x1, so you see the formula is pretty simple of geometric Brownian motion, right? X plus r minus risk free rate of sigma square plus dt, sigma and power, and z is normal distributed variable, and is multiplied with dt square. So if you really know the coding, you can say that it is same like this. It is same like this exponent, sorry, I didn't have the but it is same and mu minus sigma 2 point t, just exponent term is not there, right? For arithmetic Brownian motion, this is arithmetic Brownian motion. R minus half of sigma square dt plus sigma plus power of half of dt square root of dt into zt. And for s we just find the exponent because it is a geometric Brownian motion, and we store it in a dictionary form times and stock price, right? And we then did some plotting. It's simple plotting. uh, Made a grid, and where it is x is plotted and dt time is plotted on y-axis. And let's play with simulation, and you can see the simulation. Let me show you in more proper way. So our number of part is 25, and let's put our steps to 100. Okay, you can see the steps is not so big and the randomness is small, and you can see that some value is going below 3.8, right? But here it is not going below 50, it is following some path, right? Let me show the steps more. So you can see that the randomness increase because the number of steps increase. And yeah, maybe it is going between 3.4. Let me increase the volatility, and then you will understand the concept more better. And for this it is between 50 to 250, and you can play with the parameter. Let's say set increase the time. I am increasing the drift return. So there is a huge let's say change in geometric Brownian motion, but there is barely a change in arithmetic Brownian motion. Let us increase volatility to 100%. You can see the value is going to 2 or 4 below negative, but you can say it is never going negative. See, in geometric Brownian motion it is not going negative, and this is the Monte Carlo simulation, and it's very simple to code it, right? I hope you understood it. And parameter, I covered the parameter. The it is volatility is between 30 to 60 most of the time. And let's say correlative Brownian motion. Another project I have of is correlative Brownian motion. There is a two Brownian motion in stochastic differential equation. Let me find it. Correlative Brownian motion. Where it is? Where it is? I should pause the video before I search it. Right? Geometric simulated P measure. No. Back score, stochastic jump, correlative Brownian motion. Right. Let me first see the notebook. So see the Brownian motion is start from 0. It is between the S, and difference is normally distributed, and variance is T minus S, and non-override mean increment are independent. The formula of, so let me show you. Yes. I am so happy explaining this video. I can't even say that. I was so depressed or out of energy before recording it. I was like, please, I don't want to record it. But now I am feeling so happy. So in book, you just read the paragraph. It is pretty what's say pretty not. It is explained not it is explained very badly. So there are two Brownian motion. Let's say WT and WT1 and WT12. They both are normally distributed, and both draw from what we say by uh, bivariate normal distribution. And let me show you what is bivariate normal distribution. It's simple. I know that you can understand it is a normal distribution with both the probability, where one probability is used by one Brownian motion and another probability is doesn't used by that Brownian motion. It is like uh, condition conditional probability, like the probability of next event happening that this event is happened. Why ChatGPT sucked? Joint distribution of two random variable, like the both have same we have two random variable and there is a covariance matrix. So how covariate it is, how the relation between the both variable it is, like if mu of one process is like this, then what is the condition or what is a probability of happening this? It is a covariance correlation matrix row in between. The key parameter is, yeah, variance is this, covariance is here, marginal are normal, each xn are normal distributed, p is 0, the independent are only for normal case. So we will consider p would be 0, there is random, and then we will find the probability of correlated Brownian motion. It is correlated, it is used in jump diffusion model for like Heston jump diffusion model to find the probability, and joint density for ellipse orientation. Conditional probability is also normal, right? Say y upon x is also normal. What I say, and this is the formula. You can think like this, okay? And yeah, for this maths in this is correct. So one Brownian motion is, this is the mean term, like you can uh w1 is equal to another first Brownian motion is equal to the value of random variable from first and Brownian motion from second, and that would be covariance matrix of z1 plus covariance matrix of z2, and this value is come from the joint distribution probability, like this, where it is, I guess it is came from here, right? P, yes, it is variance, and I guess here it is variance and here it is standard deviation, right? Root x 1 minus p square, yes. Okay, the discretization version would be this. We discretize it like delta t z1 equal to delta t and p plus, this is the formula, and let's see the code. Okay, first generalize the correlative Brownian motion, set the parameter, and first 0.90, and then we will consider alter case, and you have seen the code. Normal distribution, z1 is one variable from normal distribution, second variable from normal distribution, okay, and w1 is one process, second is another process, w2 is second, time step time equal to 0, and then for loop normalized it, and then I first found the row z2 process. One variable z1 is came from normally distribution, and then we adjusted z2 with formula row covariance matrix of z1, and row is passed, I guess, right? Row is here, right? Row is the percentage change. Covariance 0.0 means there is no correlation, 9 means positive correlated, negative correlated, right? We adjusted this formula here, and this is the same formula that is written here, okay? and then then the simple Brownian motion. Okay, and then we just plot it, and you can positive correlative where rho is negative, and it is the simple plotting, negative and positive. And let me show you in app. It would be look good in app. Arithmetic or ABM, sorry, wrong app. The video has been so long. So this is step, and there is no correlation between this plot. Let me change it to negative correlation, so you can see that one random variable is going up and another random variable is going down, and it is a Brownian motion. So blue Brownian motion is going up, and second is because it is negative, it will go opposite. If it would be positive, let's say 0.9%. So let's say it is following the same path, right? The Brownian motion is following the same path. If it has a zero correlation, then it would be random. So see, it is going random. One is going up, and let me show you the random. So this is going up, this is going down, and this is going down, this is up. Like you can say it is random. Both are random. Now it is positive correlated. One is exactly same because then the correlation between will be same, and 90% in this, and negative is negatively correlated. It is huge difference. Okay, that's what I showed you. And next concept is Ito lemma. We saw the Ito process. I explained you what is the Ito lemma. So our, let's say, जो एक minute, differential equation would be ds equal to plus dz. This is our stochastic diffusion, and our lemma is tg equal to dg with respect to delta function of g. I don't know how to pronounce it. With respect to the partial derivation of g with respect to s, and there is mu s plus half of second order derivative, partial derivative of g with respect to s, and square, and s square, and that's the dt term, plus partial derivative of g with respect to s, sigma s, that is the variance term, and this formula is used. So let me tell you how it is used. Let's found a process, stochastic process of log of s. So s equal to log of s, and s is a function of x t. Log is a function of st. Another so there is no t term, right? So we ignore first t term to g. That would be g is log of s and t, right? And that would be s, and we will ignore this for simplicity. G equal to log of s, and we find the derivative. So derivative of log of x, let's say first derivative of rho g with respect to time, right? First we find the time. So there is no there is no t in it, so its derivative will be 0, right, with respect to time. You have to understand some basic calculus too. Now derivative of, where I wait a minute first. Okay, derivative of log of s, log derivative of g sparse single order with respect to s would be 1 upon x, because log x d by dx would be 1 upon x, right? 1 upon x, and the second order, the derivative of 1 of x would be minus 1 upon x square, right? G square. It is, I'm doing right, I know it. We have to have a confidence, right? Second order derivative would be 1 upon s square minus. So just we will put the value in our ethos table, right? This is the value, and our value would be 0 plus this value is 1 upon s mu s, okay, plus half, and our this value is minus 1 upon minus s square, minus 1 upon s square and sigma square, plus this value is 1 upon x sigma s or dz, and let's simplify it here. So 0 will, and this is dt, so let's 1 s with cut, so that would be mu, plus this s with cut, but there is negative sign, so this would be negative, minus negative negative half s is cut square, and this would be dt, plus 1 upon s, this s would cut, plus half dz, right? Am I doing right? Am I right? Am I right? Please somebody hear me. Yeah, I am right. That's the stochastic differential equation. 1 upon, correct, right? And you can see this in geometric Brownian motion. So see how this differential equation came to this. Forget the exponent part. Mu minus half square t upon a. So we found the solution, dynamics of this, and in this way Ito's lemma is very helpful. And log normal property, let me search the log normal property of chat, because I want to be correct. Log normal property, so stock typically model using log number, because stock price can be negative, I explained that. Returns not price are assumed log normal. So yeah, so our return, our final final output or a difference between two Brownian motion is log normal. Difference between two stock price is log normal, not stock price, right? Exponents of a normal variable is log normal. That is the property, right? Log of x equal to e upon x, right? Simple. The first year behavior property is x is normal distributed, s is log normal distributed, so the distribution would be same, but and that would be the, this formula came from Ito's lemma, right? You can see this is the arithmetic Brownian motion, and it is exponent form, and in this you can see SO is exponent of this. You have to connect the dots. The quant finance, there is so many concepts you have to understand, and you just have to connect the dots. Here it is, right? stock price is strictly positive, no negative, no normal. An exponent of st would be this, the discounted value of this. That would be simple. Variance is different, increase with time. Yeah, variance is different, like you have to remember the variance. And the momentum of the stock price is doesn't matter in modeling. Skewness, curtainess, they all have different. So curtainess is higher than normal distribution. Curtainess is the fattening, tail is fatter, right? No arbitrage price are always positive. Log number distribution are positively skewed, right? So you log number distribution. So see, normal distribution is like this, log number is like this, because the more value is on the positive side, and there is very less change in more change, what will standard deviation change. So that's why the tail is right skew image. Log number normal. You have to have a basic understanding of statistics too. It is very important. If I explain everything, then the video is already too long. I have to cut short. Yeah, I covered, and I have to also fractional Brownian motion. The book fractional Brownian motion is very confusing. So you understand the fractional Brownian motion. You, I also personally don't understood that. Fractional Brownian continuous time constant process, or it would be same. The Brownian motion memory dependence between timestamp. There is a dependence between timestamp. Okay, Hurst exponent. Yeah, in book there is a Hurst exponent given to h, right? Okay. It is called exponent 0 to 1. BH is start from 0, mean is 0. Convergence, covariance. And what is mean by covariance? Before mean self similarity is scalable, consistent, important to fraction. Wrong range, H is positive coincident. Okay, in standard they the stamp are do not depend on previous, like they are independent. But in fractional, if we are walking forward just now, they will likely keep for for moving forward momentum. Okay, h is a momentum factor, right? We are going at this speed, the momentum is reserved, right? If we our car is moving with the speed velocity of 100, and we stop the engine, then it will go with some decaying factor, right? We go some rent. That h is a Huston exponent, right? Momentum with h 0.5, or they will switch the direction, that is mean reverting. It will go to h 5, and h is, I guess, random. Okay, the fractional Brownian motion in Hurst exponent, it is derived from random normal. It is random, so we are deriving h from a random distribution. We have like a normal Brownian motion, present trending. So if h is bigger, it is trending. If h is smaller, it is anti-present, mean reverting, like zigzag. And yeah, so the expectation is 0. This is the both expectation of BHT and S, and that's the formula given in book 2, key parameter. Okay, so yeah, it is used in BS black school pricing, I guess. And yeah, this was quick introduction of Brownian motion and Ito's lemma. I hope you liked it, and I really enjoyed making this video. Thank you for watching the video, and bye bye. Keep learning.